morning, everyone, and welcome from my behalf to this talk about our experiences with assimilation of the EASI Level 2 products at ECMWF system. So I'm working for a EUMeTrain funded project where the focus is on investigating the potential of the EASI Level 2 products for assimilation, and this is done also in preparation for the arrival of NTG IRS instrument, which is the hyperspectral infrared instrument on board of a geostationary satellite, and the EASI Level 2 infrared only products will be a baseline for NTG IRS as well. But before I will share the experiences with the Level 2 assimilation, I will first shortly talk slightly about data assimilation and what kind of steps we need to do in order to introduce a new observation type into the system, and what kind of quality control and error characterization needs to be done in order to be successful in the assimilation experiments. And I have not prepared any actual interactive parts to the slides, but I would like to encourage you to interrupt me and ask questions and clarifications whenever you feel that things are not clear, or if you have questions, so not necessarily just say them to the end, but we can have discussion along the presentation all the time. So, as you probably know, ECMWF is developing a global numerical weather prediction system, and currently we are using over 400 million observations in each 12-hour assimilation window twice a day. And the vast majority of these observations are satellite measurements. So we are using radiances from geostationary satellites and polar orbiting satellites, like meteosat satellites, GOES satellites from US and so on, and then PRIS, EASI, AMSUA, MHS types of instruments from the polar orbiting satellites. Then we, of course, use also spectrometer data and GPS radio occultation, and some Level 2 products like atmospheric motion vectors, which are giving wind information that are derived from satellite images. And then radiance observations and satellite observations are the vast majority of the measurements that are used in the simulation system. But then, of course, a very important part is also the conventional observations like radio soundings, pilot observations, aircraft observations, and so on. And the radiance assimilation, together with the conventional data, are the main drivers for the headline scores. So they have the biggest impact to improve the analysis and, of course, then the forecast. And for example, from hyperspectral infrared instruments, we have thousands of channels available. So even though we get a very good positive impact through the radiance assimilation, we are not able to make use of the full spectrum of the data. So we just use a set of channels. For example, for EASI, currently it's 220 channels which are used actively from close to 8,000 channels which are available. So, and this amount of data that is available will only increase because the next generation EASI will have double the amount of channels, and NTG IRS will have close to 2,000 channels and very good temporal resolution as well. So research and investigations are all the time ongoing also on alternative approaches for the radiance assimilation. And there are some different approaches that can be applied. For example, you can use PC score assimilation, or we have very good experiences from reconstructed radiance assimilation. So the PC scores are then actually converted back into the radiance space and then assimilated as reconstructed radiances. And then Another alternative approach is to assimilate retrievals, either traditional, like temperature and humidity retrievals, or then these traditional retrievals can be transformed in a way that the error characteristics of the retrievals are possibly more favorable for assimilation. But in this study, the focus has been on traditional retrievals, so temperature and humidity retrievals, so without any transformation done. So data assimilation, the aim of data assimilation is to combine information that we have from the atmospheric state already from the model, and this is typically a short-range forecast. In the schematic figure shown in this plot, it's the blue line, so XB is illustrating the model background information or the first guess information that we have available. And then we have the latest observations, which are shown in the plot with the green dots. And the aim is to combine these two sources of information in the best optimal way to get the best estimate of the state of the atmosphere. And the main components of the assimilation system is a good forecast model, which gives us the first guess information on the background, and then a lot of good quality observations, of course, and then the assimilation algorithm, in which will combine these two sources of information. And at ECMWF, the assimilation system that we are using is a 4-dimensional variational assimilation. So the fourth dimension is the time on the x-axis in the schematic figure. So it takes into account the actual time of the observations and provides the model counterpart for the observations at the actual observation time. And the 4D var is based on minimizing the cost function J, which is here. It has two components. The first one, the B component, is the model background, so it's the blue line in this figure, and then the lower part, the R part, is the contribution from the observations, which is then the green dots in the schematic figure. And the aim is to combine these two sources of information in an optimal way. And in key role for this are the background error covariance matrix B and the observation error covariance matrix R in the equation. And when you introduce a new observation type into the system, there are two main key things that you need to focus on first. First one is the observation operator age. And this observation operator produces the model counterpart for the observations, which in the equations are marked with Y. So, for example, in radiance assimilation, the H is a radiative transfer model, and it converts the model temperature, humidity, ozone, and so on information into the radiance observations and compares the observation in the radiance space. For the level 2 retrievals, the observation operator is interpolating the model temperature and humidity and possibly ozone profile into the observation location, both in horizontal and in vertical. And then the second very important part is the errors for the observations. So both the observation errors and the correlations, because these define the weight, how much the analysis system trusts the observations compared to the model background or the first guess information that is available. And when introducing the level 2 retrievals into the system, a lot of work has been put into this observation error and error correlation derivation, and I will show you some results of that later on. The product been investigating is the infrared-only statistical retrievals from EASI, and the reason for this is that it's the baseline for NTTIRS. So I know that Thomas August has given lectures earlier this week about the level 2 products from EUMeTrain that are available, and there are different flavors, and some of them are using information from other instruments on board of Meteosat satellites in order to improve the quality of the level 2 retrievals. But at MTT, where the IRS instrument will fly, there are no supporting instruments available, so the retrievals will be based on infrared only. And the product includes atmospheric temperature, humidity, and ozone profiles, surface temperature, emissivity, and then some quality information. And our focus has been on temperature and humidity, and we have made use of the quality information available as well. The retrieval technique is based on piecewise linear regression, and the statistical training set has been taken from the ECMWF reanalysis era 5. And the data is, the retrievals are available in all sky conditions, so cloud free and cloud affected. And we have first investigated only the cloud free retrievals because that enables us to compare the results to the assimilation of EASI radiances. But then later on, we also extended the experimentation to cloud-affected retrievals. So in the last part of the talk, I will focus on the all-sky condition retrievals. So to summarize what we need to do in order to introduce new data into the system, first of all, we need the observation operator that produces the model counterpart for the observations. And for the traditional retrievals, temperature and humidity, this is just interpolation of the observation of the model temperature and humidity profiles to the observation location in horizontal and in vertical. And often the satellite retrievals are provided with so-called averaging kernels. And these averaging kernels give information about the actual vertical sensitivity of the retrieval in vertical. So we need to keep in mind that even though the temperature and humidity retrievals, they look like profiles similar to radio sound observations, for example, they are still satellite measurements, so they are very smooth, and the vertical resolution is coarse, despite there are thousands of channels available. But these averaging kernels were not available yet for this dataset that was used in this study, so I will not talk more about those, but there is an ongoing study investigating how the assimilation could be improved by using these averaging kernels, which take into account the actual vertical sensitivity of the retrievals. And then when we have the observation operator, we are able to produce the model counterpart for the observations, then we can perform a lot of quality assessment for the data, and this is very important to learn the characteristics of the data, and extremely important step to define realistic observation errors and error correlations for the observations. And when we have technically everything in place, the observation operator and the quality control and the observation errors and correlations, we are ready to move on to the assimilation trials. And it is always good to start with a simple approach. So select a set of observations where you know that the quality is relatively consistent and good, and then do the assimilation trials, because then it's easier to track down the reasons why the results are how they are and why the data is behaving in the way it is. And for the level 2 retrievals, the simple approach that we first took was to focus on clear sky retrievals over sea. And focusing on clear sky retrievals allows us to compare the results to the radiance assimilation, and over sea the quality is consistent, so that is the reason to select data over sea. And then when understanding the simple approach assimilation results, it's then easier to move step by step to more complex experimentation, and we did it for the all sky retrievals, so the cloud affected retrievals were included in the system as well later on. So before moving to the results from the quality assessment, I would like to ask if anyone has questions at this point. We saw a hand, but nothing in the chat box. But please, yes, go ahead.
Yes, can you hear me?
Yes.
Okay. Yeah, so my question is, as you said, the resolution of the IASI, the temperature and humidity. So how do you take this into account?
I'm missing words. Could you please repeat? I was missing some words from between. So the evolution of the level 2 retrievals.
Yeah, so if you have, so let's consider the temperature profile from your EASI retrieval. How many levels does it have?
It has 137 levels, so it's given actually on the ECMWF vertical coordinate.
Okay, and you use it in the same way as radio songs?
In principle, yes. So we interpolate the model temperature and humidity profiles to the observation locations in vertical and in horizontal. But then we have introduced, as I will show you later, we have introduced a very different approach to the observation errors. So we are using full error correlations, which is because the averaging kernels are not included into the product that we were using in this study. The way to take into account partly the smoothness of the profile is to take into account the full observation error correlation.
Okay, that's clear. Thank you.
Okay, thank you. Any other questions? If no, then we can move on to the quality assessment. So in the following, I will talk a lot about observation minus model background statistics, so O minus B statistics. And this is a very powerful tool. So for each observation, we can produce with the observation operator the model counterpart. And you can produce maps and zonal plots and all sorts of statistics. You can filter the data with different quality criteria, different areas, land, sea, different heights and everything. So the O minus B statistics are extremely powerful tool to investigate the quality and characteristics of the data. So in the following, it's called O minus B. And first of all, because we wanted to focus on clear sky retrievals, that retrievals are provided with the measure of cloudiness, so-called O minus C, which is the difference between the observed window channel brightness temperature and the corresponding brightness temperature computed in a clear sky assumption, with a clear sky assumption. And the figures in this slide is showing the first example of the O minus B statistics. So on the left-hand side is temperature bias, so the systematic errors, and on the right-hand side temperature standard deviation, so which is a measure for the random errors in the retrievals compared to the model background. And as you can see, both from the bias and from the standard deviation plots, that the data where the O minus C is close to 0 have the smallest bias, almost zero bias, and definitely the smallest random errors as well. And when you move to more and more cloud-affected cases, so when the O minus C goes more and more negative, both the bias and the random errors are increasing. So we wanted to focus on the best profiles in the first case, so we used the criterion for the cloudiness so that the O minus C, absolute value of the O minus C was less than 1. So that was selecting the best of the best from the retrievals for the first assimilation trials. And this slide is illustrating how applying the quality criteria affects the statistics. So the middle plot is showing the O minus B standard deviation, so the random errors for temperature, and the blue line is indicating all the data, so without any quality screening. And the random errors, especially at low levels, are quite high. And then when you apply the criteria for the cloudiness, so you only select the cloud-free cases, the random errors are indicated with red line in the middle picture. So the standard deviation decreases significantly when this criteria is applied for the data. And the retrievals, they come also with different sorts of quality indicators, and the most useful one of those was the quality indicator for temperature. And when you introduce an additional screening based on the quality indicator using a threshold of 1.5, that's the black line in the middle plot. So you can still decrease the random errors for temperature profiles. And the resulting O-P standard deviation is relatively low. So if you compare this to similar statistics calculated for radius on observations, the random errors are in magnitude roughly similar or slightly larger for the retrievals and for radius on. So that is indicating that the quality of the retrievals is relatively good when you apply strict quality criteria for the data. The left-hand side plot is showing the O-P bias, so the bias, and you can see from there that below 500 hectopascals, 600 hectopascals, there is some negative bias, even though overall the bias is relatively small. There is some negative bias, which could be a remaining cloud, but that is well, small negative bias, but still there. And then at higher levels, there is a very strong negative bias in upper stratosphere, and we found out that this is actually inherited from the training dataset from ERA 5. So depending on which model version you compare the retrievals, if you compare to the same model version which is used for ERA 5, the bias goes away. If you use a newer version than ERA 5, what has been done in this study, there is this negative bias. So it is because we don't have observations from those high levels. It is difficult to say what is actually the truth. But and different model versions behave differently at those levels. So the best thing was to decide to blacklist those very high level temperatures and not use them in the assimilation at all, because there is so much uncertainty related to those levels. And then on the right hand side, it's showing the random errors for specific humidity after the quality control and screening. And yes, also for humidity, they are of the order of same magnitude or slightly larger than for or similar statistics than radius odds. But as I mentioned, the retrievals are rather smooth, so there are some challenges for the retrievals. One of them is to capture low-level inversions. And on the left, there is example profiles. The dashed line is showing the model profile corresponding to the solid line, which is a single retrieval. So in this case, the model has quite sharp temperature inversion at low levels, which the level 2 profile is completely missing. And we calculated some statistics over the meteosat geodisk area, which are shown in the table here over winter and summer season. And overall, the conclusion is that the model is capturing a low-level inversion much more frequently than the level 2 retrieval. And our understanding is that even the model is capturing the low-level inversions less frequently than what they appear in reality. So the retrievals are capturing them very, very rarely. And the histogram here on the above the table is showing the distribution of the inversion height if they are present both in the level 2 retrievals and in the model. So the conclusion from here is that if there is a inversion in the retrieval, it is on average on higher levels than in the model. So the gray bars are indicating the retrievals, and the black bars are indicating the model inversion height. So for the assimilation, it's important to keep in mind that at low levels there are issues with smoothness, and often the inversions are missed in the retrievals. And another area where the smoothness is giving us some challenges is around the tropopause. So also the tropopause structures for the retrievals are rather smooth. And again, the left-hand side plot is showing an example profile. The model profile is shown with black, and the retrieval profile with red. So there is much more structure in the temperature in vertical in the model profile than in the retrieval profile. And the middle plot here is showing a scatter plot of the level 2 tropopause temperature compared to the model tropopause temperature. And you can see that there are two sets of observations in a way. There is a set where the agreement with the temperatures is extremely good, and then the other one where it's not good at all. And in these cases, the retrieval tropopause temperature is much colder than the model tropopause temperature. And the color scaling here is indicating a latitude. So most of these retrievals where the temperatures don't fit well with the model tropopause temperature are from mid-latitudes, but from close to tropics. And yeah, they are in the end cases like this. So in the model there is a sort of dual tropopause structure. So there is a lower tropopause and then the tropical higher tropopause, colder one above, and then the retrieval is catching only the higher tropopause. And the right-hand side figures are showing or comparing the mean tropopause height in pressure. The model tropopause is shown with black and the retrieval one in red, and the lower figure is showing the same for temperature. So on average, the model tropopause at mid-latitudes close to tropical latitudes are found from lower levels and are warmer than in the retrievals. And this is also something to keep in mind for the assimilation trials, that the structures of the retrievals are smooth, and this needs to be somehow accounted for, even though we don't have the averaging kernels yet to be used. So to summarize the quality assessment, the quality is situation and location dependent. So the best of the best data we see in cloud-free situations over sea. And the errors increase quite rapidly for cloud-affected data. And yes, overall, over land, the quality is worse than over sea. And we have introduced the quality screening criteria. So the O-C, the cloud information, is the most effective criteria to select the good quality data. And the criteria of having the O-C absolute value less than 1 represents 11% of all the data that is available. The quality indicator for temperature is also a good additional screening method. If that would be used alone, we would have like 35% of all data, including cloud-affected scenes. But then when we use the quality indicator criteria on top of the cloud screening, we end up to slightly less than 10% of all data. And this was the data set they used first for the assimilation trials. And the retrievals, as mentioned already many times, are rather smooth, so they have problems of capturing the low-level inversions and the finer scale structures of the tropopause. So the model has more often the double tropopause structure in the mid-latitudes than retrievals. And yes, these are something that needs to be taken into account in the assimilation trials. So then I will move on to the impact assessment of the retrievals in clear sky conditions. I can stop again for possible questions here if you have any. Okay, what are the reasons that the quality of sea level data is better than over land? So the data quality is more consistent over sea. The sea surface is more, there are no mountains or different kind of land below the measurement, so it's more consistent over sea, and that is the reason why also the quality is more consistent over sea. And it's easier to derive the error correlations, especially over sea when there are no big changes in the altitude, where land altitude like mountains or things like that. Okay, so the low frequency of low-level inversions captured by the ERC retrievals could be done to two effects. The training was done with data that has much less inversions than real. That is true, yes. It's our understanding that the model has less inversions than in reality. How much less inversions ERA data would have than the current operational model, those statistics I don't know. But I would not think that the difference is so drastic than what it is between the model comparison done here to the retrieval. So that could explain something, but not the big difference in the statistics. And the statistical model used is increasingly linear. I think that the non-linear statistical model, like neural networks and maybe training on real body, could improve things. Yes, that is something that Thomas and Tim Hultberg would be good persons to comment on. But then there is also that the vertical resolution of the ERC radiances is, even though there are thousands of channels, it's relatively coarse, so it can be relatively tricky to catch the inversions in the retrievals. Okay, and then there's a comment in that weather conditions, the role of humidity, water vapor, and dew is more important than the temperature, especially in the morning and at night. Yes, now that we move on to the assimilation results, you will see that we got quite nice results from assimilation of the humidity profiles, and later on in the cloud affected cases we only actually focused on the humidity profile. So there will be more information about the humidity very soon. Okay, so if I then move on to the impact assessment, then first the focus is on clear sky retrievals. So the first important step here has been estimating the observation errors in clear sky conditions, and we have applied the de Rosier method, which is the method that has been used to diagnose also the errors and error correlations for radiance assimilation. And the figures here are showing the observation errors for temperature on the left and for humidity on the right. The solid line is showing the diagnosed observation error, and then it was from the first trials it was very quickly clear that these are too small errors, so we tested many inflation factors for the errors, and resulted to inflating the temperature errors by a factor of 4. So that is quite a big inflation, but that was needed to take into account the smoothness of the tropopause structures and the low-level inversion. So you can see in the figure that at these levels the observation errors are quite much higher than in the mid-troposphere, where the quality of the data is best. For humidity, the error inflation is more moderate, so we have been using a factor of 2.5 for the humidity error inflation. And yes, defining these inflating factors are testing and trial and error. So what inflation factor brings the best result that has been chosen from a set of experiments. And with the de Rossier's method, we have also derived the observation error correlations. And these are the error correlations in clear sky conditions on the left-hand side for temperature and on the right-hand side for humidity. And you can see that especially at low levels, the correlations are quite strong in vertical. So the levels here are the ECMWF model levels from 137, which is close to the surface, up to the level 1, which is in stratosphere. And yes, the level 2 products are given on the model level, so that's why the correlations are also derived on these levels. And to emphasize the importance to take into account the full observation error correlation, I will show you some results from a single observation experiment. So we selected one profile over C in a clear sky conditions. So the ECMWF cloud detection scheme was indicating that the full ERC radiance profile was cloud-free in this location. And also the quality information that was provided with the temperature retrievals was indicating a very high quality profile. So O minus C was close to 0, so it was indicating a cloud-free profile, and the quality indicator was less than 1, so it was well below the defined threshold of 1.5. And the left-hand figure here is showing the single profile used in the single observation experiment. So the solid line is showing the retrieval temperature profile, and the dashed line is showing the model counterpart for this profile. And even though it was a good quality profile that we selected, it happened to be a case that it has both the missing low-level inversion and then a very smooth tropopause structure compared to the model profile. So the model has this dual tropopause structure while the retrieval is much more smoother here in the lower levels of the tropopause. And the right-hand side plot is showing the temperature increments. So when you assimilate this level 2 retrieval profile into the system, it makes changes to the model temperature profile, and the increments are showing the changes. So the solid line is here indicating the changes that assimilating the retrieval profile made. Yes. So, and yes, it's warming the analysis below 800 hectopascals, and then cooling the analysis above 800 below 550 or so. And for comparison, the dashed line is showing the temperature increments resulting from assimilating the same profile in radiances. So how we are doing assimilation in operations. And yes, below 450 hectopascals or so, assimilating the radiance and the retrieval are bringing more or less opposite information into the system. So the missing inversion is having a really strong signal in the assimilation and resulting these large temperature increments, which are opposite to the assimilation of the radiance profile. And this was done using a diagonal R matrix, so it was only taking into account the observation errors, but not including the observation error correlations. And when we use the full error correlation matrix, so we take into account both errors and the correlations, the temperature increments are shown here. So the dashed line is the same than in the previous plot, so the radiance assimilation, and the solid line is now the assimilation of the temperature retrieval with the full R matrix. And even though the missing inversion still results into very strong signal above 700 hectopascals, the information brought into assimilation from the retrieval is similar than the radiance assimilation. And the strength of the increments is smaller for the retrieval assimilation because we have had to inflate the errors so strongly. So radiance assimilation is bringing a larger signal into the system. So that was an example indicating how important it is to take into account the full R matrix to get right information into the system, even though the missing inversions are still causing some problems. So then we have done assimilation experiments over winter and summer season, and we have done them both in depleted observing system and in full observing system. And the reason for doing experiments in depleted observing system is that it's much easier to get a clear signal from assimilating a new observation type into the system. And in this case, the control experiment has included conventional observations and AMSU-A. So even though it's a depleted observing system, it's a very high quality baseline experiment. And then we have introduced the level 2 retrievals on top of that, and the EASI radiances on top of that. And the similar experiment has been done in full observing system as well. And this is showing an example coverage of the active data. So we have introduced similar thinning for the retrievals than for the radiances. And the quality control introduced for the retrievals, it ends up to nearly similar geographical distribution of observations in clear sky situations than for radiances. And then because of the ERA 5 inherited temperature bias at high levels, we are not using temperature data over 30 hectopascal altitudes. And these plots are showing the impact on short range forecast in depleted observing system. So these are first guess standard deviation normalized plots for first guess standard deviation for radius on temperature and humidity. So everything that is below the 100% line is indicating a positive impact, and everything that is above the 100% line is indicating degradation. So there is, and the blue line is the EASI radiance experiment, and the gray line is the level 2 retrieval experiment. So it's very clear that for temperature, the assimilation of the retrievals brings degradation into the system, but for humidity, we are able to get very similar impact than from assimilation of the radiances. So all these problems and the smoothness in the temperatures, temperature profiles, even though we take into account the full observation and correlation matrix, ends up to degradation of temperature forecasts, but then the forecast for temperatures are already very accurate, so it's quite difficult to improve them. But for humidity, there are much less observations used, and there are much more uncertainties related to the humidity forecasts. So introducing the level 2 humidity information into the system is able to improve the short range forecasts for humidity. And this is the case also in full observing system. So on the right hand side, you can see a similar plot than in the previous slide, but in the full observing system. So it's very positive to see that assimilation of the humidity retrievals can give positive impact even in full observing system. Okay, I got the message that there's only 15 minutes left, and that was a few minutes ago, so I will not spend too much on summarizing the results, but shortly, negative impact on temperature and positive impact on humidity. And because of this, we decided when moving on into the more complex cases to the cloud-affected assimilation, we decided to focus only on humidity assimilation and for now, leave the temperature retrievals out from the experimentation completely. So in the end, I will show you some results from the impact assessment of the cloud-affected humidity retrievals. So we have done, again, the experimentation in depleted observing system for the same reasons, to get a better clear signal from introducing a new observation type into the system. And then we step by step increased the cloudiness introduced into the system. So there are several experiments done, and first slightly cloud-affected data, then more and more cloud-affected data introduced into the system. And in the first place, we used observation errors and error correlations diagnosed for the cloud-free situations. And this is the starting point. So in clear sky situations, there is a positive impact on humidity, short-range forecasts of humidity. And then when we are not assimilating the temperature retrievals, only humidity retrievals, on the right-hand side plot, you can see that the impact on temperature is neutral. So no degradation for temperature when only assimilating the humidity retrievals. And then when you introduce more and more cloud into the system, you get further benefits for humidity, short-range humidity forecast that you can see on the left-hand side. But then at the same time, you start to decrease the temperature forecast when you introduce the cloud-affected humidity retrievals into the system. So we decided to modify the observation errors, and as in the beginning I showed you that the random errors are quite quickly increasing for the cloud-affected retrievals. So based on these statistics, we developed observation error model. So the more and more cloud-affected cases there are, the errors or these standard deviations, they are increasing quite linearly in different levels. So we designed this observation error model where for the cloud-affected retrievals, the observation errors increases linearly after O minus C minus 15, up to 3 times the original observation error. And then plots there are results from introducing this observation error model into the system. So we can, with the observation error model, we can keep the positive impact for humidity from the cloud-affected retrievals, and then with the gray line you can see here that the impact on temperature becomes more neutral. So there is, for assimilation of the cloud-affected retrievals, there are not anymore the big degradation on temperature forecast when using this observation error model. So it becomes more neutral for temperature, which is a nice positive result. And then the observation error correlations in these experiments, it was still the clear sky observation error correlations. So the next step to move into more complex situation was to then take into account the increased error correlations in the cloud-affected situations. So the left-hand side plot is showing the error correlation for cloud-free retrievals, humidity retrievals, and then the right-hand side plot is showing an example for diagnosed error correlations for cloud-affected one, which are very much cloud-affected. So you can see that the error correlations increase significantly for the cloud-affected retrievals, as well as the observation errors. So we developed also a model to modify the observation error correlations. So depending on the cloud amount, there's an inflation factor that we apply for the clear sky error correlation, and then end up to the inflated R. So depending on how much cloud there is in the scene, then we inflate a little bit or a lot the error correlation matrix in the assimilation. And that is also quite nice result. So we can obtain further benefits from introducing the scene-dependent observation errors and error correlations. And in this case, the control run is using the level 2 retrievals with clear sky errors and error correlations. So it is the starting point for the cloud-affected retrievals. And then the blue line is indicating the experiments where we use the scene-dependent observation errors but clear sky error correlation. So we get a small improvement for humidity forecast compared to the already good impact that we got in this case in the control run. We get improvement from modifying the observation errors, and then further improvements when we use the scene-dependent observation error correlations. So it's moving step by step to more complex cases and taking into account the errors that we can get further and further positive impact from the humidity retrievals. But it's also an example that using satellite retrievals is definitely not like using radius observations. The error characteristics are very different, so it's very important to take these error characteristics into account when assimilating the retrievals. So quickly to summarize the assimilation of the cloud-affected humidity retrievals. So they overall assimilating the humidity retrievals brings improvements to the short-range humidity forecast, but then using the clear sky observation errors degrades the temperature forecasts when assimilating the cloud-affected humidity when there is quite a lot of cloud in the scene. But this can be improved by using the modified observation error model and error correlations. And the good thing here is also that the results are consistent in full and depleted system experiments. So here I only showed the depleted observing system experiments, but we saw positive impact also in the full system experiments, which is quite nice. And it's also different because in the radiance assimilation we only focus on clear sky radiances for EASI. So this is something that is not present in the system currently in operations. And I'm sorry that I was rushing in the end, but hopefully there are time for some questions still.